what you'll see is it doesn't go much beyond 6,000, right? See, there's -6 and +6. It goes a little past. There's a slope that it goes up, but oh, wait, 6,000? I thought we had 10,000. Maybe this one doesn't form a plastic hinge. Let's look at the other ones. Yeah. So all three of them didn't form a hinge, but this one did. I don't know which one's which now. But you can see how this is the moment versus time. And it went to 60,000 when we ran linear elastic, and now running nonlinear, it's hitting, goes along, and then at some point hits 10,000, and it's -10. It doesn't go much beyond that. And you can see if you zoom in that it's like a square wave when it hits it, and then it's following that second slope, right? So it goes a little bit above it. Let's look at between, let's say, 16 and 30 seconds. I go to here. Right here, it's at 10, see, and then 10, just it doesn't continue on like that. This is linear elastic, this line will just continue all the way to, well, it went all the way to 6 times larger, right? So this is the actual response over time. Moment. I don't remember which one. Let's see, it's probably this one. Yeah, that's 38, so it's the bottom of that. Let's see what this one is. This is 42. Oh. That's interesting. So forming a plastic hinge here caused it to not form one at the top. When if it's linear elastic, both top and bottom look like they would go nonlinear. But the fact that you're allowing the bottom to essentially form like a hinge, then the added moment, it didn't go all the way to 10,000 at the top. And then this one here was, what was it, 46? 47. 47. Okay, let's look at that. Here's 47. Let's take out 38 for a second. Oh. Yeah, it's look at that. Hits 10 and then holds it for that much time and then unloads again. And then cycles back and forth without being at 10, but then every once in a while it hits 10 in both directions. Now, if you want to see the moment rotation response, this is the Takeda model, which is similar to a pivot model that I developed. And we can say display, and then say show a hinge result. So this is just the moment rotation response at all the plastic hinges. So there's one of them. This is at 38. That's the one at the bottom, right? Or, yeah. Was it? So, I'm going to get out again. Or move this or something. Let's see, this. That's at the bottom there. This was 42. And the other one. So there are only 3 here. Display, show hinge results. So if I run this, it starts at this point here, 0, 0. And as I'm moving, this is moment versus rotation. So it's rigid at first, right? It's going straight up and down. And then you see as I'm moving across in time, now look, it's going up, down, boom. And now look, suddenly it's, it goes these large excursions here, and then it's cycling around like that. It's following the rules. I can see, looking at this is correct. It's following the right moment rotation rules of the Takeda hysteresis. It's very different from elastoplastic if you use the other rules. It yields, it goes this way, and then unloads, and goes all the way around here, and then yields this way, and then goes all the way. So it's taking a lot more energy out of the system than a reinforced concrete section. This is much more realistic. Mine's kind of similar to this in terms of the amount of energy taken out of the system. Let's look at 42. Oh wait, before we go to the other one, I did want to show you something else. So you can show the backbone that we gave it. Here, see that line? So that's the envelope that this is supposed to follow. Then there are hysteresis rules that it follows when it cycles back and forth. It's not just going monotonically. But to give you a sense of scale, you can click the second one, and you can see it's actually not that far compared to what I said, that this is the full curve. This is failure, rotation failure, and this is So it's not getting very, even on this side, you see it gets to here, I have a lot more capacity. But that's assuming 0.1 rotation, that's a lot of plastic rotation. If it was 0.04 or 0.05, then based on what I define, then it'd be back here somewhere, right? And it would get closer to failure. Okay, so now let's look at, I'll turn the scale off for now, that looks a little neater. Let's look at the other one at 42. That's interesting. This is showing that it's reaching, it must be, I don't know, I must have been looking at the wrong thing before. But this is definitely forming a plastic hinge at the top of that first one. And then, but let's see the scale. So it's going out about the same amount as at the bottom, a little less. And then the other one, 47. This is at the top of the member that's pinned at the bottom. Now that's kind of a neat plot. Let's turn this off for a second. Look at that. You get a sense of the hysteresis rule in this particular plot. If you go out like this, and then it unloads on the square root of deformation, but it affects the initial stiffness. So because it's rigid, it looks like it's still vertical here because of that. But then what it'll do is it'll go to the prior shoot to the prior maximum, which is this point here. Then it unloads, and then it goes to the prior maximum there. So that's, you can see like what it's doing here, this occurred before this point, so what it's doing is heading toward that point there. And that's all it's doing. So rather than having full square loops, it's much less energy in each side.
Failure is defined as when the first steel breaks.
Failure is when you reach a rotation capacity. So when your ultimate curvature is reached, and it's translated to plastic rotation. And that could be when your vertical rebar fails or your transverse rebar fails. The transverse rebar fails really is represented when your concrete reaches its compression strain capacity. So whichever one occurs first.
We also consider the concrete progression.
Yes. That's what I was just saying. The transverse concrete crushing, I mean, it's really defined by your transverse reinforcement, right? You equate the, based on Manor model, you equate the transverse reinforcement capacity. That's how you get the ultimate compression strain capacity. So that's when we say that the velocity or you reach your compression strain capacity, it's really failure of the transverse reinforcement. So it's actually a reinforcement in both cases. But you're looking at your tensile strain capacity of your vertical primary reinforcement or your compression strain capacity of the concrete. The compression strain capacity is defined by your transverse reinforcement. So once that fails, once it fractures the transverse reinforcement, then you reach your compression strain capacity. If you have no transverse reinforcement, then the compression strain capacity is probably 0.004. Unconfined. Let's see. What else? Let's open up. I guess I can unlock this now. Unless is there anything else you want to see while we're in this? Because if I unlock it, we lose 1 hour of runtime. I can't get it right now.
It's just a 2D analysis.
Yeah, it's just this. Remember, this is the model that was restrained transversely. And that's fine. If you want to design a bridge like this, I'm happy with that. It doesn't have to be full 3D. Some bridges, you can't do it 2D. It has to be 3D depending on the geometry. But if you can do it this way, no point in wasting time doing everything in 3D. In that case, then your wind loading would only be the longitudinal aspect of it. Seismic would only be longitudinal. Yeah?
Is it generally like a significant difference of 3D, superstructure rotation?
No, in this case it would just be, it's not so much that. In the 2D, in the direction this way and everything else I think is fine. It would only be, first of all, if the bridge is curved in plan view, then it would make a big difference. But if you have loading earthquake coming in and out of the page, then that's completely different. That's what I mean. Then it could be different. If you have single column vents, they act like a cantilever this way. Longitudinally, it's fixed, or fixed. I'm just thinking if there's anything else of interest. I think that's it. Let's unlock it. Okay. Now let's say define function. I just want to show you response spectrum. Let's bring on the new one, say from file. So this is the one that Toyan posted and that I put on Blackboard now. Add new function. And then I'm going to browse and find it. I'll call this Caltrans. This is the magnitude 8 earthquake. Browse. So I have to find it wherever I put it. Project. And then it's the text files. So there it is. Caltrans magnitude 8. I think that's what it's called. Okay, and then you have to view file before you plot it, because there's some header lines, 1, 2, 3 header lines, and this gives you the information. Magnitude 8, period 0.7 G, that's the peak ground acceleration. On the left, that's the starting point. Okay, so 3, that's all we needed now. So header lines